So we're in section 14.4, and we are now moving up by one dimension and integrating over a three-dimensional patch of real estate. And of course, you know, integrating over one variable was hard enough, and integrating with two variables was even harder. And of course, we're going to even compound it more by doing it in three dimensions. But folks, once you have mastered the techniques from double integration, then triple integration is just a step up from that. Just an extension of what you've already been doing from the double integral. All right, so we're going to be just integrating with respect to the x, y, and z here in the section 14.4. When we get to 14.5, we're going to be using the other coordinate systems of the cylindrical and spherical coordinate systems. So just for the x, y, z coordinate system, the little elements that we are thinking about are going to be basically rectangular objects of dimensions delta x, delta y, delta z. And just like we've developed, your definite integrals in 1 and 2 dimensions, we let delta x and delta y go to 0 to get you your dx element or your dx dy element here. We're going to let your delta x, delta y, delta z go to 0 so that your dv element will just be dx, dy, dz in some order. It could be dy, dx, dz, or dz, dy, dx, or whatever. So your dv element, your little tiny differential element in three dimensions is what we call the dv element, d capital V, is something involving the dx, the dy, and the dz. So what we're kind of thinking about is integrating over a three-dimensional space. This three-dimensional space could look something like this, where in this example you have z varying between these two surfaces in a sort of vertical sense. Maybe z is bounded below by this surface here, given by the equation z equals g of xy. Maybe z is bounded above by this surface up here, z is equal to h of xy, whatever, some two variable function. And then you project that conglomeration of three-dimensional stuff down onto the xy plane. Once you've figured out your limits for z, now you can figure out your limits for x and y down here on the xy plane, which you already know how to do from double integration. You can figure out a function of y in terms of x or x in terms of y to establish your limits for y and then for x or vice versa. So that's kind of what we're talking about here. If we're going to evaluate the triple integral of a three-variable function dv over this three-dimensional region that we're calling d here, you have to decide, do you want to integrate with respect to z first, or with respect to x, or with respect to y? If you decide to integrate with respect to z first, then z will go from here to here, and then you'll figure out your limits and integration for x and y down here on the xy plane. So there's just kind of an expansion of what we were talking about here. So z varies between here and here. And then like I said, once you figure out your limits for z, now it's just up to your x and y variables on the xy plane. So it could be that you integrate with respect to y first, where y varies from here to here, and then you integrate with respect to x, where x will go from here to here. That's what. And so you will end up with a three integrals. The innermost integral will be having limits involving potentially functions of two variables. And then the second or the middle integral will have limits involving just one variable, the outer variable, so to speak. And then the outermost integral will have constant limits. Worst case scenario, of course. It very well could be, though, that you integrate over a box, in which case you have constant limits for all three variables. Now, we evaluate our triple integrals in an iterated sense, meaning one integral at a time. You integrate the innermost integral first with respect to whatever this variable is. In this case, it happens to be z. So you would integrate this integrand function with respect to z first, and then evaluate between the upper and lower limits. Notice if you integrate with respect to z first, and you evaluate between the upper and lower limits, then you're going to end up with a function that you can now do a double integral of with respect to x and y. Then you, in this case, you integrate with respect to y and x, evaluate between the upper and lower limit, leaving you just with a function of x. And you integrate with respect to x and evaluate between these two constant limits, and you end up with just a number. Now, how do we interpret that number? Well, how did we interpret the value of your double integral? Well, we interpret that as the volume, between these two surfaces, or above the xy plane, but below a surface, in 3 dimensions for a double integral. So how could we think about this triple integral? Well, we would have to think about what would be like a 4-dimensional sort of volume. Hyperspace, right? Hyperspace volume. Hard to visualize, but it's at least the 4-dimensional analog. So, all right, well, let's take a quick example here. This is example number 1. Take a quick peek at integration. This one happens to be where we're going to integrate over a 3-dimensional volume. Let's kind of go skip forward to see what we're going to integrate over. We are going to find the mass of this box. Now, the mass happens to be variable. A function of z, not mass, but the density, I should say. The density happens to be a function of z, but we're going to integrate over this 3-dimensional box. And we're going to evaluate this triple integral. So here we've got the density that we're going to integrate over this 3-dimensional region. So here because of the fact that this is a rectangular box, we could choose to integrate with respect to z first, with respect to y second, and then with respect to x last. You're just working your way from the inside out. But we could just as easily integrate with respect to x first, then with respect to y, then with respect to z. It doesn't really matter in this example. In some cases, you have a certain order that makes more sense than some other order. But in this case, we could choose to integrate with respect to z, where z is going to vary between 0 and 1. And once you figure out your limits for the one variable, then you project that shape into the coordinate plane for the other two variables. In this case, once we figured out the limits for z, then we could project that 3-dimensional shape onto the xy plane. Now we have this 2-dimensional region, and we have to decide, do we integrate with respect to x first and then with respect to y, or vice versa. It looks like we're going to integrate with respect to y. Y is going to vary between 0 and 2, and then x will go from 0 to 3. And then voila, we've got our triple integral. Setting up the integral is the hard part. Not to say that evaluating all your triple integrals is going to be easy, because some of them get to be really long and tedious. I distinctly remember 20 years ago as a calculus 3 student, and I would just do my work on the paper that I would get from the computer lab. And back in the day, the computer lab would have those foldy green sheets from those pinwheel cartridges. If you've ever seen those before, have you ever seen those? Probably. Those are all passing now in a museum. But those would be those accordion sort of folding. You know what I'm talking about there. And I would just do my work on there because those darn triple integrals would just take so long. I would just turn on my homework. I would just kind of fold it up, 8.5 by 11 sheet, turn it in. Hey, it's good, recycling. Of course, today's a whole lot different now, huh? But just understand that some of these triple integrals can take a while. Very tedious, some of them. All right, so we figure out those limits of integration. So what does that work out to be? Let's go ahead and work out that triple integral. So we're going to do the, let me get my pen fired up here. So we're calculating the mass, and so we calculate the mass by integrating the density function. That density function happened to be given by 2 minus z. And remember, we were integrating with respect to z first, and then with respect to y, and then with respect to x. And remember, z varied from 0 to 1, and y varied from 0 to 2, and that x varied from 0 to 3. Now, your next step would be to integrate the integrand with respect to z. So you're going to have 2z minus 1/2 z squared. Evaluate from 0 to 1. Now you plug in 1 for z and plug in 0 for z. Of course, when you plug 0 in for z, you don't get anything. So you're just, when you plug in 1 for z, you're going to get 2 minus 1/2, which is 3/2. And then you integrate with respect to y, and you're just going to get 3/2 y, evaluate from 0 to 2, which is going to give you 3/2 times 2, which is 3. So I'm just going to write 0 to 3 times 3 dx. And when you integrate with respect to x, you're going to get 3x. Evaluate from 0 to 3, you're going to get 3 times 3, which is 9. Okay? So in the interest of space, I'll skip with some steps. But you understand the process? Okay. An important thing in evaluating these multiple integrals is that when you integrate with respect to one variable, you hold the other variables as constants. And that's not an easy thing to remember if this is really the first time that you're doing it. It just takes some practice. So let's take now a look at example 2. Really not much I'm going to write down, at least right away. Now, when you're asked to find the volume of a three-dimensional object, if you know the two-variable function whose graph is up top, then you can integrate that function. Otherwise, you can integrate in triple integral just the function 1 over that three-variable, three-dimensional space. So suppose that we want to find the volume of this wedge shape. Now, we could do the double integral of the function 6 over this two-dimensional region down here. Or we could just take the triple integral of 1 over this three-dimensional wedge. No big deal. So how do we do that? Now, you want to identify the most difficult limits of integration, honestly, first, and do those. Now, you're going to see that x varies from 0 to 6. Y is going to vary from 0 to 4 minus 2x. 4 minus 2x is the equation for this plane right here. And then x is going to go from 0 to 2. Now, how do you set up your integral? Well, let's choose to integrate with respect to y first. Y is going to go from 0 to 4 minus 2x, like you see in our green little arrow. That'll be our first integration, our first limits of integration. Y goes from 0 to 4 minus 2x. Now, we could choose to let z go from 0 to 6 next. Or we could just as well let x go from 0 to 2. It doesn't matter. In this example, we're going to let x go from 0 to 2. And then lastly, we're going to let z go from 0 to 6. So here we've got this triple integral right here, which calculates that three-dimensional volume. Everybody see how that goes? Any questions on how that goes? So let's go ahead and evaluate that integral. So that volume was triple integral, see, dy, dx, dz. Y went from 0 to 4 minus 2x. X went from 0 to 2. And z went from 0 to 6. So let's integrate with respect to y first. And of course, y is going to go from 0 to 4 minus 2x. Okay. And then integrate with respect to x next. And you're going to get what? 4x minus x squared. Evaluate from 0 to 2. And plug in 2 for x. And you're going to have 8 minus 4, which is 4 dx. And then integrate with respect to, hold on, this last one is z. Sorry about that. Z. Integrate with respect to z. Z is going to go from 0 to 6, and you're going to get 24. Okay. So 24 cubic units is the volume of that wedge. Any questions on that? All right, here is another example where we could use a triple integral. We're going to use the triple integral to find the volume of this three-dimensional region that's bounded to the left by y equals x squared plus z squared, which is a paraboloid, and then bounded to the right by this other paraboloid, y equals 16 minus 3x squared minus z squared. So what is this volume? I don't know, it could be a tank or something, a tank for fluid or something. So the y thing would be for us to integrate with respect to y first, where y is going to vary between the left and the right surfaces. So that's clear enough. But then, when we project the shape onto the xz plane, what does that shape look like? It's kind of like a shadow. Imagine if I had a big floodlight and shone, is that the right tense for that verb? Shone it from the, I shined it, I should say, shined it from the right to the left. And what is the shadow that results? It's this region that you're going to integrate over on the xz plane. So how is that region defined? Well, what we need to do is figure out what is this region of intersection between these two surfaces. So basically what you need to do is set these two functions of x and z equal to each other. Because they're going to meet at the same y value. So you have x squared plus z squared is equal to 16 minus 3x squared minus z squared. And just do a little bit of arithmetic. You might get, 4x squared plus 2z squared is equal to 16. Divide out the 2 so that you've got 2x squared plus z squared is equal to 8. Aha! Well, that is the equation for an ellipse. And in particular, that's the equation for this ellipse on the xy plane. So then you could choose to solve for z in terms of x or x in terms of z. You choose. In this example, we've chosen to solve for z in terms of x to get lower and upper limits. So when we take that equation, solve for z, of course, we're going to have z squared is equal to 8 minus 2x squared, and then take plus and minus square roots in order to get the lower half and the upper half. So z on the xy plane, z is going to vary between negative square root of 8 minus 2 minus x squared and positive square root of 8 minus 2x squared. So that's why you see these limits for the z variable. And then finally, x is going to vary between negative 2 and positive 2. And as promised, the innermost limits of integration have two variables. The middle limits of integration have just one variable. And then the outermost limits of integration just have constants. Now, carrying out this integration, I'm just going to let you take a look at the bottom of page 1020 and invite you to do that yourself on your own. But it works out to be 32 pi times the square root of 2. So take a look on page 1020 for all the gory details. And they don't even show all the details. You have to understand that you have to, do basically a trig substitution for the final step. Okay? Is there any way you want me to go through all the dirty details of evaluating the integral? Okay, that's good. That's kind of like my style anyway. I like to talk about general ideas and let you read up on the details. Unless you have any questions, of course. Sound good? Sometimes you have set up your triple integral and find out that you can't actually integrate it as it is. So how do you do it? Let's take a look at example 4. And you're given this triple integral. Integral from 0 to the 4th root of pi, 0 to z, and y to z. And you're integrating the function 12 times y squared times z cubed times the sine of x to the 4th dx dy dz. Now, the region that you're integrating over in 3 dimensions is defined by those limits of integration. So, x is going to vary between y and z. Y is going to vary between 0 and z. And z is going to vary between 0 and the 4th root of pi. Let's take a look at the picture. It's really hard to visualize that, isn't it? So you got to try to figure out how to sketch it in 3 dimensions. So here's kind of what it looks like here. So you've got this plane that comes out like this, and then you've got another plane that goes in like that. And then it's topped off horizontally with plane z equals 4th root of pi. Now, according to the limits of integration from the original triple integral, let's see here. X varied from y to z. So just pick some point on the YZ plane, and then you saw that x is going to come out like this. It's going to enter this kind of like this diagonal plane and exit this plane right here that's going out like that. So on the back end, x is going to be entering the plane x equals y. And on the exit, it's going to exit through the plane x equals z. And then so once you figure out those limits for x, and then you're going to project that shape then onto the YZ plane. And the projection of that shape onto the YZ plane is what you see in the yellow. And then, the next step was to integrate with respect to y, where y went from here out to here. Now this line turns out to be, y equals z. And then the limits for z is from 0 to 4 through pi. What's the problem, though? Let's go back. Why cannot we integrate this? Why can't we carry out this integral just as it is? Anyone want to hazard a guess? Well, when you integrate this whole thing with respect to x, now 12y squared z cubed is a constant with respect to x. And in order for you to integrate the sine x to the fourth, you need to get, some factor of x involving x cubed, in order to do a substitution or an x squared or something. You need to be able to pick up some factor involving some multiple or power of x in order to do a substitution. So, what to do? Well, is to change limits of integration so that when you do your first or your innermost integral, that it's going to involve a limit involving x. That's what you need to do. So here's what we're going to do. We're going to choose, when we rewrite this and change the limits of integration, we are going to integrate with respect to y first. Now, for this same three-dimensional region, we're going to now let y vary from, now, on the xz plane, that's where that boundary is on that side. It's just flat on the xz plane. So, x is going to vary from, y, I should say. Y is going to vary from 0 out to this plane. This plane right here is the plane y equals x. So y is going to vary from 0 to x. And those are going to be the limits for your innermost integral. Now, once you've fixed those limits for the y variable, then you project that shape onto the xz plane. And there's the projection of that shape on the xz plane. And then you sort out your limits for your integration between x and z, right? Well, we could choose to let x now vary from 0 to z, and then z will go from 0 to 4 through to pi. So now we have our triple integral with the correct order. So let's go back to my previous slide here. So now let's see. Sorry about that. So now here's that integral with the rewritten limits of integration. It's the same integrand. So this hasn't changed, but the order of integration is now dy, dx, dz. Now remember, y varied from 0 to x varied from 0 to z, and then z varied from 0 to 4 through to pi. Now, do you see what's going to happen when we integrate with respect to y? Now, I'm just going to do this first step, and I'll let you carry out the rest of the steps. So again, these things could take a long time. But when we integrate with respect to y, the innermost integral there, this part right here is going to be what? 4y cubed, z cubed, sine of x to the fourth. Evaluate it between 0 and x. dx dz. Now, essentially what's going to happen now is you're going to plug in that x for y. So now you'll have your 4x cubed, z cubed, sine of x to the fourth, dx dz. Now, do you see your next step? You integrate with respect to x, you're going to do a clever substitution by letting u be equal to x to the fourth. du is going to be 4x cubed, and then everything happy and so forth. Okay? Dot, dot, dot. Carry on. And I guess that really worked out to be, I'll let you finish this up on your own, and that worked out to be pi over 4. Okay? Anybody want me to work out the details? Okay. Well, I mean, if you do, let me know. Okay. All right. Working out the average value of a function is the same that we learned from the one variable case and the two variable case. Same thing applies. Analogously, in 3 dimensions, you just basically will integrate your 3 variable function over the given 3-dimensional region and then divide the value of that integral by the volume of the region that you integrated over. So as our final example, which we're just going to do a flyby on, this is example 5, where suppose that we've got a block of conducting material occupying the region D is equal to 0 to 2, 0 to 2, 0 to 1 for x, y, and z respectively. So you can see that at the top of the example here. And due to heat sources on its boundaries, the temperature in the block is given by this 3-variable function is equal to 250 xy times sine of pi z. So what is the average temperature? So to find the average temperature over this region D, and that region was given by this definition, it's basically a rectangular block. So average temperature, so you're basically going to integrate over that block. So average temp. So again, you choose your limits of integration, but in this case, you're integrating over rectangular blocks, and the limits are pretty, constant like, right? Now, by the way, what is the volume of this box right here? 0 to 2, 0 to 2, 0 to 1. 2 times 2 times 1 is 4, right? So going to divide by 4 and then integrate your temperature function. Now, you want to choose a variable that you want to integrate over, x, y, or z. How about z? You want to integrate with respect to z? No problem. Z varies from 0 to 1. How about integrating with respect to x next? No problem. X goes from 0 to 2. Integrate with respect to y last? No problem. Y goes from 0 to 2. All right, so your next move is to integrate this function with respect to pi.
Oh, I'm sorry, with respect to z, of course. I was seeing that pi there. So integrate basically the sine of pi z function, which will give you what your negative cosine pi z divided by pi, and so forth. And then integrate with respect to x, and then the integrate with respect to y. It's pretty easy, folks. I'll let you work out the details. And of course, all the steps are in the textbook. All right. Does anybody want me to work out the details? Think you got it? All right. Moving along here. Folks, I know that it's kind of warm and stuffy in here, but if I open that door, it's going to be even more hot and steamy. So this is as comfortable as it's going to get. So, all right. Does anybody need to take a little bathroom break or anything, or you want to keep on going? Does anybody need to take a potty break or anything? All right, let's go. Now we're still talking about triple integrals here in section 14.5, but at this time we're going to take a look at integrating using the cylindrical coordinate system and the spherical coordinate system. It's still three variables for each one of them. It's just that these variables could actually be useful, more useful than the other coordinate system. Like, for example, integrating over a spherical region or an ellipsoid, I don't even know how to say it right, ellipsoidal region or that sort of thing. Some of those weird round sort of regions in three-dimensional space are better used in or handled using other coordinate systems instead of the XYZ rectangular system. We're going to first start off with the cylindrical coordinate system. Cylindrical coordinate system is basically the polar system together with the z variable. Now, look down here on the XY plane, and to locate your x and y coordinates, you would know how to do that. But instead, measure the distance from the origin out to the point on the XY plane. And that's going to be r. Theta is going to be the angle made between that radial element and the positive x-axis. So r comma theta, that we know and love from polar coordinates on the xy plane. And then, of course, the z variable will tell us how far above or below you are with respect to the xy plane. Now, r is just agreed, let's all agree by convention that r is never going to be negative. R is going to be 0 here at the origin, what they call the pole. Otherwise, r is going to be some positive number, but never negative. Theta is going to be some angle between 0 and 2 pi. And z, of course, could be negative or positive, any real number will do. Okay. So if you are comfortable with the polar coordinate system, then the cylindrical coordinate system is a piece of cake. Now here are some popular surfaces in cylindrical coordinate. First of all, we have the cylinder. Now x squared plus y squared equals a fixed number, right? But x squared plus y squared is equals some numbers. That's a circle, right? In other words, r is equal to some fixed number without respect to what the z is, right? So there's your cylinder. It's just basically an infinitely long tube that goes up or down with the fixed radius a. A could be any positive number. You could have a cylindrical shell where r varies between two numbers. A is the smaller number, b is the larger number. So there is your surface in cylindrical coordinates. R is, greater than or equal to A, less than or equal to B. You could have a half plane, and in cylindrical coordinates, it's given by the equation theta is equal to some number.
That number being the angle that that plane makes with the positive x-axis. You could have a horizontal plane like this, where the z variable is fixed, independent of the angle, so z equals a is the equation for that plane in cylindrical coordinates. So you could see that there are some advantages. Now, z equals a is the same thing as z equals a in both coordinate systems. But you could see with just saying that theta is equal to pi over 3 or whatever is a lot easier to say than saying arc tangent of y over x in cylindrical or in rectangular coordinates for the plane. So using these alternative coordinate systems confers some simplicity, right? Some benefits of simplicity, but making that transition from one coordinate system to the next, so can be a bit of a challenge. Understand. Here we've got a cone, and we define that cone in cylindrical coordinate system by saying that z is going to be some multiple of r. So the larger that you go further away on the xy plane from the pole, the larger the z is going to be. And it's just going to go in a linear fashion. And that's pretty cool, huh? Think about what the equation for a cone is in rectangular coordinate system. Remember what it is? Something like z is equal to square root of x squared plus y squared. A lot nastier. So you can see the benefit of using the cylindrical coordinate system. So let's take a look at example number 1. How can, for example, number 1, part A, identify and sketch the following sets. For part A, we're going to take a look at R goes from 1 to 3, Z is going to be positive, or at least non-negative. And that's what part A is, that's the leftmost one. So R goes from 1 to 3, and Z is non-negative. So no surprise here. There's the innermost core, that's R equals 1. The outermost wall is at R equals 3. And by having R go from 1 to 3, that means that the inside is hollow. And it doesn't extend below the XY plane, but it goes up forever. This next one is the surface, it's S, given by where Z is equal to 1 minus R, and R is going to go from 0 to 1. So Z is equal to 1 minus R. Of course, we don't want Z to mean what, negative or anything. So when R is equal to 0, Z is equal to 1. When R is equal to 1, when R is equal to 1 out here, then Z is equal to 0. So it looks like one of those dog collar things. Have you ever had your dog operated on? They put the cone of shame on them, right? Something like that, so you can model it. Except you could use this equation, except instead of letting R go from 0 to 1, if you just want this top part locked off, you could choose for R to start off with adding a number greater than 0. And that'll only bring you so far.
Okay. Now, how to convert between rectangular and your cylindrical coordinates? Remember that. So here on the xy plane, r is going to be the distance from the origin out to the point projected down on the xy plane. Angle theta is going to be the angle made between that radial element and the positive x-axis. So we can kind of go in the opposite direction. So if we know r and if we know theta, then the x-coordinate is given by r cosine theta. The y-coordinate is given by r sine theta. And r, of course, squared root of x squared plus y squared. Tangent of theta is equal to y over x. So if you know y and x, then you can figure out theta. Depending on, of course, what quadrant of the plane that the point on the xy plane is, of course. That's why we don't say that theta is equal to arc tangent y over x. It's going to be arc tangent y over x. You know, you might have to add pi or something, or subtract pi, depending on what quadrant. All right, so there's the conversion back and forth between the rectangular coordinate system Did you guys need some time?
No worries.
Need it?
Sorry.
Okay.
You just tell me how it goes.
Okay. So you can convert back and forth between the rectangular and cylindrical coordinate systems. All right, so there's the conversion. Any questions on that? It's basically for polar, but together with the z coordinate. All right, moving along here. The dv element in cylindrical coordinate system is basically going to be the dA element for polar, r dr d theta, together with the z. So you're going to have r dr d theta dz. Really, that's really what it works out to be. So nothing really magical. It's pretty simple. Okay, so moving along here. And of course, your generalized three-dimensional object here, how do you integrate with respect to cylindrical coordinates? Well, it could be that the z variable varies between two functions of x and y, like you see here. So convert over to polar for your x and y coordinates, and then you'll have your upper and lower limits for z in terms of r and theta. It's really what it works out to be. So then we'll project that shape down onto the xy plane, and now onto the polar plane, I should say, and then you figure your limits in terms of polar coordinates on the xy plane. Okay? Really what it comes down to. Okay, so remember our triple integrals are iterated. And so if you remember our discussion from 14.5 or whatever, the previous section, it's the same discussion except instead of using x, y, and z, we're using z, r, and theta. Okay, now, a lot of times we integrate with respect to z first, but we don't always. Sometimes we integrate with respect to r. We rarely integrate with respect to theta. But always, always, always make sure that you bring in that factor of r with your dv element for the cylindrical coordinates. Just like you would with the polar integrals for your double polar integrals. But if you integrate with respect to z first, z could be a function of r and theta, so for your upper and lower limits. And it could be that r is going to be a function of theta for your intermediate integral and so forth. All right, moving along here. So this is example 2. So the idea here was to take a look at, if you take a look at the integral, and I should have given you some room, take a look at example 2 on page 1030. This is going to be the integrals of square root of 1 plus x squared plus y squared over this region right here.
Now, notice that this region is basically a semicircle stretched, right? In the vertical sense.
Now you're integrating the square root of what? 1 plus x squared plus y squared. That integral is just screaming out to be evaluated in cylindrical coordinates.
Because take a look at it, that's just a portion of a cylinder, huh? So to evaluate that more complicated integral, just switch to polar. Your x squared plus y squared is going to be equal to r squared. And you're going to, integrate with respect to z, where z varies between -1 and 2. That's nice, constant limits of integration for z. And your limits for little r, and look, it's a circle, right? It's a semicircle. So r is going to go from 0 out to the edge of the circle, which is going to have a constant radius of, I guess it works out.
Let's see, let's go to the next slide.
That circle has a radius of 2√2 when you work it out from doing the switch over to the limits of integration. And then theta is going to go from, what, -π/2 to +π/2? So it's always desirable to have an integral with constant limits of integration. So when you look at this triple integral here, this is like a dream come true compared to the original integral that they start off by giving us at the beginning of example number 2. So switching over from rectangular to cylindrical basically means that you're just switching over to polar for the x and y coordinates. And your limits will oftentimes be a lot more simple. Any questions about what we did here? And of course, this is a nice, beautiful triple integral that you know how to solve. It involves 3 variables. Then you go boom, boom, boom. You just integrate with respect to r first. See, you got the square root of 1 plus r squared. You do a little substitution, let u equal 1 plus r squared. And then here's your r factor that you can use with your,
when you do your substitution, okay? No problem. So I'll let you work out the value of that triple integral. I'm moving on here. Give you guys maximum time for your exam here. Let's take a look at example number 3. So here we are asked to find the mass of this object. Now they're telling us that the density of this object is given by 5 minus z. So it's most dense up top. I should say, no, actually as you go from the bottom to the top, the density decreases. So it's most dense at the bottom, and the density decreases as you go from the bottom to the top. So 5 minus z is the density. So what's the mass of that? So basically you integrate the density function over this 3-dimensional region. So this 3-dimensional region is basically defined by, cylindrical coordinates, defined by z equals 4 minus r squared. In rectangular coordinates, that would be z equals 4 minus x squared minus y squared. But in cylindrical coordinates, it was a lot more simple. So how do we integrate the density function in cylindrical coordinates? Well, we can integrate with respect to z first. Z is going to go from 0 to the surface, which is 4 minus r squared. And then, now once we figure out the limits for z, then project that whole shape onto the polar plane. And then that shadow is just now the circle of radius what? Well, at
when z is equal to 0, 4 minus r squared is 0. That means that r squared is equal to 4. That means r is 2, right? So now we have the circle r equals 2, huh? Down here on the polar plane. So r is going to go from 0 to 2. Theta is going to go from 0 to 2 pi.
So now we have our triple integral.
So the triple integral would calculate the mass. We're going to integrate the density function over the three-dimensional region. Z is going to go from 0 to up to the surface, 4 minus r squared. And then r is going to go from 0 to 2. Theta is going to go from 0 to 2 pi. Don't forget in your dV element that you have your r in with your dr and theta. So you might see it tucked in there, but make sure that you pull it out and bring it in together with the rest of the integrand. But it's a common mistake to forget about that guy.
So let's go ahead and do that calculation here. It's not too bad. So that mass, 0 to 2 pi, 0 to 2, 0 to 4 minus r squared, 5 minus z, dz dr, which I'm going to write r dz dr d theta. So bring that r out so we don't forget about it. Bring that r out from here to be with the rest of the integrand. Now let's integrate with respect to z first. So of course r is a constant with respect to z, so you'll have r times 5z minus 1/2 z squared. And then z is going to go from 0 to 4 minus r squared. We have dr d theta. So we'll do the first couple lines of this triple integral. And then wherever you see z, substitute in the 4 minus r squared. All right, and now your next step is to take this expression involving r and simplify. Simplify and then integrate. And don't forget our d theta there, and integrate. Integrate, evaluate between 0 and 2, and then you don't see your limits as being functions of theta in this case. So you could also drop this outer limit this multiplied by 2 pi, if you want. And then I'll let you finish that up. So that worked out to be, when you simplified this, of course, I guess that worked out to be 24r minus 2r cubed minus r to the 5th power. And that is including that factor of r there as well. So you have this as your next step, really. dr d theta. So like I said, you go through and integrate with respect to r. Integrate with respect to r, you got 12r squared minus 1/2 r to the 4th power minus 1/6 r to the 6th power. Evaluate between 0 and 2, and you can just go ahead and multiply by 2 pi for the theta that went from 0 to 2 pi. And of course, when you plug in 2, you got 12 times 2 squared minus 1/2 times 2 to the 4th power minus 1/6 times 2 to the 6th power times 2 pi. And I guess that works, the whole shebang works out to be 88 pi over 3. But I ask you to go ahead and work that out yourself independently and see if you can verify that. Or better yet, just get those big stacks of scratch paper. Have a ball. All right, here's another example here. We'll just look at it real quickly here.
Because after you've seen a few triple integrals, you pretty much get it, right? Okay, so here we're going to, for example, number 4, find the volume between two surfaces. So below this paraboloid here and above this cone. So it would seem natural to integrate with respect to z first. Z is going to go from this bottom surface to this top surface. All right, so once you figure out those limits for z, this guy, and then project down onto the xy plane, you're integrating over a circle. Polar, right? Meaning you should be using a cylindrical coordinate. So replace the x squared plus y squared by r squared. So really this cone is going to be z equals r. This paraboloid is equal 12 minus r squared. On the plane, r is going to go from 0 to whatever the outer edge. How do you know what the radius of the circle is? Well, shoot, set 12 minus r squared equal to r, and it's just an algebra problem to solve for r. And it works out that the positive solution to that equation works out to be r equals 3. So the circle is a radius 3. R goes from 0 to 3. Theta goes from 0 to 2 pi. And we've got our triple integral, which then calculates that. So the integral that calculates this volume is integral of 1 dz dr d theta with an r factored in as part of the integral. Z goes from r, 12 minus r squared, theta goes from 0 to 2 pi, r goes from 0 to 3. Okay. All right, now let's move on to our next coordinate system. Now, let's just take a step back real quick. With the rectangular coordinate system, we can locate any point in space using 3 linear measurements. So many units in the x direction, so many units in the y direction, so many units in the z direction. So 3 linear measurements. 3 linear dimensions. In the cylindrical coordinate system, you needed to know 2 linear measurements and an angular measurement. Well, with the spherical coordinate system, you need to know 2 angles and a linear measurement. So, let me show you a picture and then I'll come back to this. Here's what we're looking at here. We can locate a point in 3-dimensional space by first finding the direct linear distance, otherwise known as the radial distance, from the origin out to that point. And that distance is called rho, Greek letter rho, as in r, as in radius, right? And then you have this angle phi, which is the angle between the positive z-axis and that radial element, or that radial line segment from the origin out to that point. That's what phi is. That's one of your measurements. Notice, by the way, that phi is going to go from 0 down to pi over 2, in which case you would be on the plane, on the horizontal plane, I should say, and then it could even go down to the negative z-axis, which would give you pi. Right? That's but phi is never going to go beyond pi. So phi is going to go from 0 to pi. Rho is, of course, going to be from 0 to whatever, infinity. Now, theta is our friend. We know and love our theta. It's the same guy that we've been dealing with all along for our polar coordinates. If you were to take our point in 3 dimensions and project it directly down onto the xy plane, and then draw a radial line segment from the origin out to that point on the plane, then theta will be that angular measurement between the positive x-axis and that radial segment, line segment on the plane. So theta, you already know. Rho, you pretty much can understand it as the 3-dimensional
distance as the crow flies between the origin and the point. And then phi is that angle there, which is a little bit exotic at first. Now, how do you convert between spherical and rectangular? That's on this slide right here. Now, because of the fact that that rho measures the distance between the origin and the point, we know the distance formula, right? So square root of x squared plus y squared plus z squared. So we have the conversion between rho, or rho squared, and x squared plus y squared plus z squared. So we know how to find rho. Rho is then the square root of x squared plus y squared plus z squared. And you can do a little bit of trigonometry to find the two angles. Now, if you know the two angles in rho, then you can find x, y, and z. So let me explain these. Let you write these down if you want. They're in the textbook otherwise. So here's the slide that explains where these conversions from spherical to rectangular come. All right, so we have rho, right? Now, and this is phi. Imagine if you were to go directly across from your point to the z-axis, and you have this right triangle here. So cosine of phi is going to be the z-coordinate over rho. That's why rho times cosine of phi is equal to z. Now, so we were talking about cosine of phi. The sine of phi is going to be this distance up here. You see where I'm pointing at here? Sine of phi is going to be this distance here divided by rho. Meaning that's the same distance as that you see here on the xy plane. If you were to project this point down on the xy plane, then rho sine phi is what measures the distance between the origin and this point projection. And then if you take rho sine phi times sine of theta, then you've got this distance right here, which is basically the y coordinate. And if you take the rho sine phi times cosine of theta, then you've got this distance right here, which will give you the x coordinate. So that's the reason why you've got those conversions between spherical and rectangular. So it looks kind of strange, I know. Now, if you know x, y, z, and you want to convert to rho, of course, rho is the square root of x squared plus y squared plus z squared. Phi is going to be maybe the, if you know z, you can then take the arc cosine of z over the square root of x squared plus y squared plus z squared. And then, you of course, tangent of x over y is going to be theta, that sort of thing. So you can just use your trigonometry skills to figure out, to get from rectangular to spherical, to get your phi and theta angles. Okay, here are some popular surfaces in spherical coordinate. If you want to place a ball of some sort above the plane, a units and radius A, then you could write that with this equation here. Rho is equal to 2a cosine phi. In fact, you could even have a ball, centered at the origin with rho being equal to some constant value. But if you want to shift it up so many units with the radius equal to the center's displacement from the origin, then here's your equation. Now, imagine trying to write that in rectangular coordinates. It'd be a lot more complicated. Here, if you want your surface up here, this is the surface z equals 4. It's a lot more simple in rectangular and cylindrical coordinates. But, hey, if you want your surface at 4 units above, we could write that as z equals 4. But remember the relationship between rho, phi, and z. So, but even in spherical coordinates, the equation is not too bad. Like I said, if you want your sphere centered at the origin with a fixed radius, then the rho equals that number, equals that radius, will be your surface. If you want your cone, just tell me the angle. And phi equals that number. Phi equals that angle will tell you what that cone is. Of course, rho will go from 0 to infinity, and theta will go from 0 to 2 pi, but phi will be fixed. If you want your half plane, your vertical half plane, theta is still going to be fixed at a number. If you want your horizontal plane, we already saw a specific example, but rho equals a secant phi. Cylinder of a fixed radius. So rho equals that radius times cosecant phi. So we already saw our sphere sitting on top of the plane, or we can shift it downwards if you want, adjusting appropriately. What does the dv element look like in spherical coordinates? It'll turn out to be rho squared sine phi rho d phi d theta. I'm not trying saying that 3 times fast with a mouthful of salt and crackers hanging on your head. But that's what it is, rho squared sine phi rho d phi d theta. Where does it all come from? Well, without going into a whole lot of gory details, it involves basically knowing the relationship for a circle's sector remember the sector. If you want to know this arc length right here, S is going to be equal to the radius times the angular displacement, where that angular displacement is in radians. So take a look, here is our little dv element here. So we're talking about this distance right here times this distance. And then times that distance right here. So basically put everything together involving the 2 angular pieces, like this piece and this piece right here, that which both of those links involve this sort of calculation for arc length. And then together with your d rho, right there, that's why you get your rho squared sine phi d rho d phi d theta. We'll see a more intuitive way when we do our conversion of coordinate systems when we get back together on Thursday as well, instead of the geometric argument instead. So, how do we integrate in spherical coordinates? Well, a lot of times rho is going to be a function of the 2 angles, phi and theta. So you let rho go from the
innermost to the outermost surface, right, between G and H. And then you figure your limits for the two angles. And let's just really hope that the limits for the two angles are going to be constant. But I've seen it where some of these nasty triple integrals that I've worked with in the past where phi is going to be a function of theta and so forth. You'll see very little of that in this class, but because otherwise I would be expecting for you to have a couple hours of your life to devote to that. And that's the intention, is just for you to understand the basic ideas of this without putting you through a whole lot of pain and discomfort. So just kind of understand that, look, this is any other triple integral, just using a different coordinate system. So basically what this picture shows is that for once you figured out the limits for rho, then you, if you can imagine it, project that shape onto the theta phi sort of coordinate system plane and figure out your limits for theta and phi. And most time, at least for what you're going to be doing in this class, those limits will be constant. A lot of times rho is going to be a function of only phi. A lot of times theta is just going to have nice constant limits of integration. But it doesn't have to be that way, of course. So here, just a different view of what we just saw. Rho varied between two surfaces, which are functions of phi and theta. And then once, like I said, you figure out those limits for rho, then you have your nice, easy, constant limits for phi. Looks like phi is going to vary between here and here, between these two limits here. On the lower limit up here and the upper limit down here. And then theta is going to vary between here and here. You have to do even more intense 3D visualization, though. Who are the electrical engineering students here? Anybody? Yeah. You're going to love this system. Now, keep in mind, especially my EE people, that they don't always use rho. Sometimes they use R in your EE textbook. And what we use as phi, they might use theta. And what we see as theta, they might use as phi, or some other angle like alpha or something. So make sure that when you are studying out a textbook and they decide to use spherical coordinates, that you know exactly what symbol is being used for which dimension in the spherical coordinate system. Otherwise, if you don't take the time to figure that out, you might be lost in the sauce. Okay. All right. So we need to take a look. What does our spherical triple integral looks like? Well, just like any other triple integral, you've got your three-dimensional function, your three-variable function that contains your rho, phi, and theta. And then your dv element is your rho squared sine phi d rho d phi d theta. Not necessarily in this order, but 90+% of the time you'll integrate with respect to rho first, and then phi, and then theta. Yeah, I know, it looks like a mess, but you have to make sure, though, that you always bring in your rho squared sine phi, and then factor that into your integrand. If you don't, then you'll be wrong. Let's do an example here. Number 6. So we're going to take a look at this triple integral
integrate over some three-dimensional piece of real estate called D, and the function that we're going to integrate is x squared plus y squared plus z squared raised to the negative 3/2 power dv. So that's the integral we're going to integrate. In that region D, in spherical coordinates, because it's easier to write in spherical than any other coordinate system. So it looks like rho is going to go from 1 to 2. Phi is going to go from 0 to pi over 2. And theta is going to go from 0 to pi over 2. So what does this look like? Well, rho goes from 1 to 2. That means that all the points in this region are going to be between 1 and 2 units away from the origin, like you see here. Now, you see the blue part, that forms kind of the inner wall, beyond which it's hollow. But it's solid between 1 unit away and 2 units away, so in this yellow region, if you can visualize. See, too bad I can't have three-dimensional graphics here, and you could all put your three-dimensional glasses on there. It'd be kind of cool. Maybe someday we'll have a technology to do that. Now, phi is going to go from 0 to pi over 2. And theta is going to go from 0 to pi over 2. Remember, this is 0 for theta, and this is pi over 2. So everybody understand how this is that region D that we just described? So how do we set up our triple integral? First of all, that x squared plus y squared plus z squared for the integrand is just rho squared. And then we could let rho go from 1 to 2 as our innermost integral, and then phi could go from 0 to pi over 2, theta goes from 0 to pi over 2, and we're done. Imagine doing that in rectangular coordinates. It would be a mess, huh? You could do it, but it'd be a lot more difficult than in spherical coordinate system. But because after all, you're integrating over a portion of a sphere, huh? A portion of a solid sphere. This is essentially a rectangular block in spherical coordinate system with constant limits of integration for all three variables. So what does that variable look like? Well, what does that integral look like? Well, remember, we're integrating x squared plus y squared plus z squared to the negative 3/2 power. So that's the function that we're integrating. To convert that to spherical, we just simply will substitute rho squared in place of the x squared plus y squared plus z squared. So you have rho squared raised to the negative 3/2 power. So that just basically gives you what? Rho to the negative 3 power, huh? So then we're going to go ahead and integrate that function of rho to the negative 3 power. And don't forget, you have your rho squared sine phi d rho d phi d theta as your dv element. This whole thing right here is your dv element. Now, rho for this example went from 1 to 2. Phi went from 0 to pi over 2, and theta went from 0 to pi over 2. So let's go ahead and make our next step here. And now, when you combine those two terms involving rho, you just get rho to the negative 1 power. So you integrate that, what do you get? You get natural log of rho, huh? Evaluate it from 1 to 2, huh? And so forth. D phi and d theta. So, and then you just So you do your evaluation, you'll just get a number, and then integrate with respect to phi, that's just going to wind up with pi over 2 times whatever this is, and then integrate with respect to theta, getting yet a different number. So what does that work out to be? I guess that works out to be verify the details, pi times natural log of 2 over 2. Okay? All right, moving along here. All right, this is our last example this evening, and we're going to find the volume of this ice cream cone. This ice cream cone here. So we're going to integrate the function 1. So we just now need to figure out the limits for rho, phi, and theta. And the good news is that it's simple, at least in spherical coordinates. Because here, for the upper part of this dome here, rho is fixed. Now, we need to find the volume of the solid region D that lies inside the cone. Phi equals pi over 6. And rho equals 4. So rho equals 4 is going to be the radius of this dome. So distance from the origin to any point on the yellow surface is 4. So what is the volume? The volume is going to be equal to, we're integrating the function 1, and here's your dV element, rho squared sine phi d rho, d phi, d theta. Now, rho is going to go from 0 to 4. Now, phi is going to go from 0 out to pi over 6. 0 to pi over 6. And then theta, so once you project this whole thing down onto the xy plane, and you look at the region that gets swept out by theta, theta just goes all the way around in the circle. 0 to 2 pi. And that's really the hardest part about any triple integral, regardless of the coordinate system, is setting up the limits of integration. And that's it. Once you've got this set up, it's an easy integral to solve. You just work your way from the inside out. And what does that work out to be? You do your first integral with respect to phi, to rho, I mean, and then integrate with respect to phi, and then integrate with respect to theta. And the whole thing works out to be 64 pi over 3 times 2 minus square root of 3. Would anyone like for me to go through the details of this integral? Or do you think you got it? Okay, all right. Your choice. Make sure, though, that you study the steps on page 1038, though. See if there's anything new that you can pick up. All right, so any questions about the cylindrical and spherical coordinates? All right. I'm going to give you until 1/4 till to take your break, get refreshed and stuff, and put everything away and get ready to take the test. And then we'll get started at 1/4 till. And then you'll have the rest of the class period. Okay? So take care. See you in 10 minutes.